let's continue. So let's look a few more minutes in this graph. And then so what we see? We see that in this graph we have on one side we have q square minus 1 over q minus 1 points. It's q square plus q plus 1. On the other side we have exactly the same number of points, q square over q minus 1 points on this side. And now let's see what's the degree of this graph. If we start with a vertex here, so a vertex here is a one-dimensional subspace, right? Inside the total is fq cubed, right? So the total dimension is 3, and a point on this side, right? This is the dimension 1. This is the dimension equal to. A point on this side is connect to all the two-dimensional subspaces containing it. How many of them we have? By the homomorphism theorem, right? This is exactly the same as the number, if this is W and this is V, so this is exactly in one correspondence with the subspaces of V mod W, which is isomorphic to fq squared, right?
They're non-trivial.
Well, the non-trivial, right? It's the non-trivial subspaces here, namely those of dimension 1 in the quotient. These are those of dimension 2 here. The number of them we know is q plus 1. So every space here is, the degree of it is q plus 1, right? Every vertex. And on the other side is also q plus 1. Because here if we have W, which is a two-dimensional, the number of one-dimensional subspaces of it is also q plus 1. And so this is a q plus 1 regular graph. Well, we could also reduce it by duality if you want. You know, taking for every space its dual, give you some kind of an automorphism of this graph from one side to another. So this is a bipartite q plus 1 regular graph. Okay? So now, let's see what is, now let A be the adjacency matrix of it. Now, the adjacency matrix of a bipartite graph, if I put, you know, I put here the dimension 1 and then I put those of dimension 2, then because all the edges are going from dimension 1 to dimension 2, then this is 0, and this is 0, and this is, say, some matrix B, which represent the adjacency between 1 and 2, and if you check, well, the matrix is symmetric, so here it must be B transpose, right? So if we take now, if we want to compute eigenvalues, then that's basically like the trick I showed you. In a bipartite graph, sometimes the easiest way to compute its eigenvalues, instead of computing the eigenvalues of A, to compute the eigenvalues of A squared. So let's see what is A squared here. On one end, A squared, if you take something like that, 0, 0, say here is B and here is BT, and multiply it by, well, here it's the blocks are even all of the same size, so it's BT 0, so this is equal to BBT, BT 0, 0, and BTB. And the BBT and BTB And you remember that a square really represents the graph of going from here to here and back, well, two paths. But then when you do two paths, so here is like 1 and 2. So this part is starting at 1, going to 2, and coming back to 1. That's why we get only on this side. That's the combinatorial meaning of that. And this is, we start in a point in 2, and we take a path of length 2, starting in a vertex of dimension 2. Then we go to dimension 1, and we come back to dimension 2. Right, so that's what we get. Well, you remember that the eigenvalues of this and this are the same except of zeros. But in a minute we'll see there are no zeros here, so they are really the same. But more important, let me claim, that's an easy claim, but let's see, that a square is equal to q plus 1 identity plus j minus I, which is equal to qi plus j, where j is the all ones matrix. So it's a matrix such that everything is 1, 1, 1, 1. Let's see why. Proof. Think about the graph. What does it mean to go by a path of length 2? Or as we say, a square really represents a new graph. Maybe graph with loops, maybe graph with double edges, but you go from one side to the other and you come back. So first of all, you can go from a vertex here to the neighbor and come back with the same edge. Right? And this you will do q plus 1 times. So this gives you the contribution of q plus 1, the identity. So like in the graph a square, there are q plus 1 loops. You go and you come back to the same loop. Right? And think of a square as representing a new graph. It's a graph on the same set of vertices, and we say that we put an edge between a vertex to another one, or to itself, if there is a path of length 2 going from the first to the second. But if it's the same one, then there are q plus 1 such path. I can go and come back immediately with the same path. But I can also go and I can go from here to here and come back to another one. And now here is the point. If I want to go to another one, there is a path of length 2 and there is a unique path. Why? This is exactly the axiom of the projective geometry. Every 2 points, you remember, if you think of it as a vertex versus, as vertices versus lines of the projective plane, points versus lines of the projective plane, every 2 different points are contained in a unique projective line. Or, simply in the linear algebra terms, every 2 one-dimensional spaces are contained in a unique 2-dimensional space. Okay? Simply the space generated by them, spanned by them, is 2-dimensional, that's the only one. Therefore, there is a unique path. So there is a unique path going from every 2 different, and this gives you the metric j minus I, right? Because you can go from each one to the other one. Well, I'm sorry. I'm sorry, that's not the right way to do it. I have to be careful. This is when I'm doing it here. This is it's a square upper and a square lower. It's the same thing, but I'm getting it twice. What I mean, this is the upper where it is. Yeah, this is A squared upper, and this is A squared lower. Right? If I do it only on those of this side, that's what I get. Are you with me? It's okay. So that's when I start with those dimension 1 going back and forth, I'm getting exactly BBT. So BBT, if you want, is equal to this. And but BTB is also equal to this, which is not so surprising because if you check, this is a symmetric matrix, right? So anyway, BTB is the transpose of BBT. And if this is symmetric, then they are really equal to each other. What?
No. This is an separation.
This is what? What's the problem?
It's not the transpose of each other. It turns out to be, but it's not.
Each one is a transpose of itself.
It turns out to
BBT
be.
is the transpose of itself?
In this case, it
It
turns
turns
out
out to be.
Yeah, sorry, okay, not because it just turned out to be the same, sorry. Yeah, right. Okay. It turned out to be, and now it's exactly the same. If you start with dimension 2, then you have q plus 1 ways. If you start at this side, you have q plus 1 ways to go back and forth from every vertex on this side. And every different 2, there is a unique one connecting them because every 2 subspaces, every 2 different subspaces of dimension 2 intersects in exactly one-dimensional space. Okay? Okay, so now it's fairly simple to compute the eigenvalues because this is, now what is the matrix J? The matrix J is, so this is, so what are the eigenvalues? So eigenvalues of A squared, it's twice, everything will be twice eigenvalues of Qi plus J. Now, eigenvalues of J are what? J, okay, now okay, which J is this? No, the J is a matrix of just one side, right? It's J, it's the 1, 1 on that side. Okay? It's like the size of J is not the complete one, is only this size, right? This size. So J is QQ minus 1 divided by Q plus 1 matrix with eigenvalue, that number, Q minus 1, which is Q squared plus Q plus 1, on the constant function, 1, 1, 1, 1, right? If you multiply by the matrix 1, 1, 1, 1 by this matrix 1, 1, 1, 1, 1, then you just sum it up, right? And you got this eigenvalue. On all the rest, it's 0, right? And on the orthogonal complement, what is the orthogonal complement? Is all the functions, all the vector space, such that the sum up of them is 0. But that's exactly what J is doing. On the orthogonal complement, this is what's called rank 1 matrix, namely it really lives only on one-dimensional space, and on the orthogonal complement of it is really acting like 0. The orthogonal complement, I don't know, what should I call it, U, which is all the x1 up to xn in up to x, the right number, right? Q minus 1 divided by Q minus 1. In R, Q minus 1 divided by Q minus 1, such that sigma xi is equal to 0, this is exactly the sum, but that's exactly what the matrix. Complement J restricted to U is really equal to the zero map. Because J multiplying by J, just summing up the coordinate. That's what J does, right? It's a matrix. So now Q is a scalar matrix, which is commuting with J. So the eigenvalues Qi commutes with J. So now it's very easy to compute eigenvalues. So eigenvalues of Qi plus J is, well, we take the one eigenvalue of J, which is Q squared plus Q plus 1, plus Q, and here 0 plus Q. So this is with multiplicity 1. And this is all the rest. Okay? And here, now, here is a little miracle. What is Q squared plus Q plus 1 plus Q? This is Q squared plus 2Q plus 1, which is equal to Q plus 1 squared. Okay? And here we are getting Q. So the eigenvalues here will be Q plus 1 squared, which should be, right? Because the matrix A we started with is a matrix of a Q plus 1 regular graph. So we knew that it has Q plus 1 as an eigenvalue, then A squared must have the eigenvalue Q plus 1 squared. And indeed, it comes up. It's okay, it's a very simple computation. And it did come up, and all the others are just Q. So what we get, let me write it twice. Each one of these appears twice, and then Q, so this is like multiplicity 1, and this is Q all the rest. Okay? So now, what are the eigenvalues? What are the eigenvalues of A? I take square roots of these. So, eigenvalues of A, well, I have to take Q plus 1, 2 roots of it. Which roots I will take? The positive one or the negative one? Both, each one once. Why? Because you remember that for a bipartite graph, every the spectrum is symmetric. I think this I showed, right? I showed that the spectrum of a bipartite graph is symmetric, right? If lambda is an eigenvalue, then minus lambda is an eigenvalue, and I even showed you how to get from the eigenfunction from lambda how to get an eigenfunction to the minus lambda. So you can even see that the multiplicity is the same because you can kind of associate the eigenvalues, the eigenvectors, right? Not just that if lambda is minus lambda, but even with the same multiplicity. I mean, maybe I didn't say it, but it follows from the proof. So the eigenvalues of A are plus minus Q plus 1, and then each of multiplicity 1. Well, it must be because, well, the graph is connected, right? So Q plus 1 will appear only once. And then plus or minus square root of Q, and this is with equal multiplicities. And if you really want, I can tell you exactly how many, like plus minus square root will appear, well, let's see, each with multiplicity, well, we know that the size is 2q squared plus q plus 1. We divide minus 2, divide by 2, and then we get q squared plus q. So we computed completely all the eigenvalues of this graph. You see why? Is it clear or it was not? It's completely elementary, but it was a good exercise. I want to show you that this kind of axiom with projective geometry, if you want, really gives you the full information about the eigenvalues in this case.
Is the computation of the eigenvalues of the Laplacian are
Well, in this case not, because in this case the Laplacian is nothing more than q plus 1I minus a, and they commute, so there is no problem. If you will, when it start to be, in the next example, we start to have some difficulties. Maybe I plan to do many other things today on this next time. Okay, maybe I'll do the next example just to give you a feeling that that's still, but maybe even before that, when we are talking, did he manage to talk about Ramanujan? Did he say what are Ramanujan graphs? Did I tell you what are Ramanujan graphs?
Last class.
What?
I think last class. I think last class, yeah.
I said this? I defined Ramanujan graphs?
I think so, yeah.
Ah, okay, so. you're the only one who remember. Okay.
No.
What?
Uriah just proved Shigeru inequality.
But he didn't, and Alombo-Pana theorem, did we mention Alombo-Pana theorem?
No.
Okay, let me for your education, let me mention it in passing for a second, because these are Ramanujan graphs. These are, in some sense, the easiest examples of Ramanujan graph, and it looks, in the first sight, that they contradict Alombo-Pana theorem. So let me take 5 minutes and give you the definition. Definition, a finite K regular graph is called Ramanujan graph if we know the second if a finite, say, connected, if every eigenvalue lambda of A, the adjacency matrix, satisfy either lambda with absolute value is equal to k. So it can be either k or minus k. K is always an eigenvalue, remember. Minus k is an eigenvalue if and only if it's a bipartite. Or if not, then it's very small, or lambda is less or equal to square root of k minus 1. Now, why this number k minus 1, square root of k minus 1 here comes into the game? I will not give you the full explanation here. I'll just say that I'll just quote the theorem of Alombo-Pana. So first of all, okay, just a moment. Example: these S2Q are Ramanujan. Why? Because
It's 3.
what?
3, not 2.
Thank you. Why? Because they are Q plus 1 regular graphs. Right? They are Q plus 1 regular graph. And the largest eigenvalue is Q plus 1. So all the others should be less than 2 square root of Q. And they are indeed less than because they are even square root of Q. Right? So these are Ramanujan. Now, but you might say that we are contradicting the following theorem of Alombo-Pana. Alombo-Pana theorems tell you that you cannot do better than than Ramanujan. But let's write it carefully. Alombo-Pana theorem says that if xn n goes from 1 to infinity is a family of k regular graphs with the size of them going to infinity, then the lim inf even of lambda 1 of xn, I don't remember if I called it before, lambda 1 is the second largest eigenvalue. So that's a family of connected sets, but the second largest eigenvalue of xn. Namely, the largest one we all know, this is k. The question is, what is the second largest? The second largest, Uriah showed you that that's a very important eigenvalue. That's the eigenvalue which is responsible for the expansion, right? If this second eigenvalue is very small, then these are good expanders, then they expand well. All right, so we want it to be as small as possible. Now, even if you take the limit, if you take a subsequence, such that the best you want the lambda 1 to be as small as possible, it won't help you. So Ramanujan are fantastic, right? In Ramanujan, they are something like 2 square roots, much less than k. But the Alombo-Pana tells you that this is greater or equal to square root of k minus 1. So you can never win the Ramanujan. The Ramanujan is like the optimal expanders in this sense. But you might think that this is a counterexample, right? Because here we got not 2 square root of k minus 1, we got that the second eigenvalue is square root of k minus 1. But it's not a contradiction to the Alombo-Pana theorem, because the Alombo-Pana theorem is true for fixed k. That's an important thing to notice and to remember. For a fixed k, you cannot win. You cannot overcome the Alombo-Pana bound, or if you want the Ramanujan. You can win when k is going to infinity. You can arrange smaller and smaller. Which is not so surprising, because if you, for example, if you take the complete, if you will take the complete graph, then the complete graph is of course the best expander. It's just that it's the degree is huge, right? And the degree, then the second eigenvalue is 0. That's the best expander, of course. And it's Ramanujan, of course. And it's beats Alombo-Pana, but but k is not fixed. So Alombo-Pana is really for a fixed k, then we get it. We cannot beat the 2 square root of k minus 1. Okay, but if k is not fixed, then we can get. Okay. Now I wonder, you know what? I don't think I will start really what was supposed to be the main. But let's look at the next example, which is much more complicated. If we just go to dimension 4, you will see that the situation is getting more and more complicated, but also more interesting. So let's take the n equal 4, and let's look what is now S4 cubed. Also a very interesting simplicial complex. Now, what are the vertices of this complex? Now we have 3 types of vertices, right? What will be the dimension here? The dimension here is going to be 2-dimensional. So that's really the first time we are going higher than graph. It's going to be a 2-dimensional vector space. It's going to be, it is a 4-dimensional space, and we we have now dimension 1, we have dimension 2, dimension 2, and then we have dimension 3. Well, the reason I did dimension 2 slightly higher, because there are so many more spaces of dimension 2 than in dimension 1 and 3. So let's see, the number of dimension 1 spaces, well, that's easy to compute. This is q to the 4 minus 1 divided by q minus 1. It's the same computation as before, which is equal q plus q plus 1. The number of dimension 3 is the same, right? By duality, we don't even have to compute. What? Sorry. But now let's see what the number of dimension 2, and so this is what we called before 4 over 2q, and this is just an example how to compute it, and you can easily generalize it. How do you compute how many subspaces you have of dimension 2? You do the following. You count how many, every subspace of dimension 2 is spanned by 2 linearly independent vectors. So I first of all look how many pairs I have of 2 linearly independent vectors. So I can choose the first vector in q to the 4 minus 1 ways, because I have to choose any vector which is non-zero. And then the second vector should be linearly independent of the first one. So it should be not in the one-dimensional space spanned by the first vector. Okay, so this is q to the 4 minus q. So this is the number of pairs which generate a two-dimensional space. But I want not to count the number of pairs. I want to count the number of two-dimensional spaces. So I have to, which means that many pairs will give me the same space. How many pairs will give me the same space, the same two-dimensional space, is exactly like the number of bases of two-dimensional vector space. So I have to divide by the order of GL2, or if you want, by the number of bases to fq squared, to a two-dimensional square. Okay? So this gives me the number of pairs. I don't think I have to write it in so detail, right? I mean, this is the number of pairs of independent vectors, Each such pair give me a two-dimensional space. But the same two-dimensional space is obtained from quite a number of these. How many? Exactly the number of bases that a two-dimensional vector space has. A vector space of dimension 2, this is the number of bases it has. You choose the first vector in q square minus 1 ways, and then you choose the second vector in q square minus 2 ways, and this is precisely the number. And this is, okay, so if you want, this is q 4 minus 1 divided by this, and this is q squared plus 1, and this is, now we can divide both by q, then q cubed minus 1 divided by q minus 1. This is q squared plus 1 times q plus q plus 1. What is important for me to see that this is approximately something like q to the 4th, while these are approximately q to the, so this is something like the main term is q to the cube, here the main term is q to the 4th, and here again the main term is q to the cube. So you see that here in the middle we have many more vertices than in the two sides. Okay, now let's compute the degrees. Like so this is going to be a two-dimensional complex, right? We are going to have triangles here. What are triangles in this complex? Triangles in this complex are exactly a set of three subspaces that one is contained in another, right? One-dimensional inside two-dimensional inside three-dimensional. Okay, so now let's see what the degree of every vertex here. So what the degree? I have to ask myself two questions. How many edges are going from here to here? But I also have how many edges are going from here to here. Right? So for every one-dimensional space, I have to ask myself in how many subspaces of dimension 2 it touches, and how many of dimension 3 it touches. But that's very easy. Why? Because what does it mean to have an edge here? It means that this subspace W is inside here and inside here. So I can look at the full space, which is dimension 4. I divide it by W, what I'm getting, a space of dimension 3, and the number of, and the two-dimensional spaces containing W are in a one-to-one correspondence with the one-dimensional spaces of the quotient, right? Again, the homomorphism theorem, what is called, what we call it in the elementary course, corresponding theorem between subgroups of the quotients and subgroups up containing the kernel. So the degree here is equal to the number of one-dimensional spaces in the three-dimensional space. So this is 3 over 1 Q in our notation. These are the white edges plus 3 over 2 Q, which they are really equal to each other. Because the number of one-dimensional subspace in 3 dimension is equal to the 2 dimension in 3 dimension. And we know to compute it. This is something we already compute. This is 2Q squared plus Q plus 1. So the degree here is like that.
I think it's in our notation it's K13 and K.
What?
We have notations for.
Just a second. I want to relate it to the regularity, but just a second. But that's the degree of this graph as a graph, first of all. How many edges are coming from it? Now let's look now. So by duality, you understand, and if you don't, you think about it, the degree here is the same. Is also 2Q squared plus Q plus 1. Everything is kind of upside down. We can take, for every flake, we can take the dual flake and take it ups and down. I mean, there is always a symmetry to this. But let's see what is the degree of here. That's actually even easier to compute, but it's a different number. You take a subspace of dimension 2, and you ask yourself, how many edges are going from it to this side, and how many are going to that side? The number of edges going from it to the left is the number of subspaces of dimension 1 it contains. Right? So the degree here is Q plus 1 to here because it contains Q plus 1 of them. But at the degree to the other side is also Q plus 1 because a space of dimension 2 inside a vector space of dimension 4 is contained in exactly Q plus 1 subspaces of dimension 3. So the degree here is only 2Q plus 1. So you see, and if you compute, this will be fine because every you see there are many more points on the middle, many more, because you see something like, you remember, q to the 4. But the degree of each one of them is only around q. While here in the two sides you have less points, but the degree of them is q squared. Okay? Now, so this is regular and irregular. It's irregular if we would not take, you see, regularity. You see, if we would think of it as a regular graph, then it's not a regular graph. But if we think of it as a complex, you remember I started and I showed you that in general, S and Q is always a regular complex because we count it as a regularity with colors. And I don't want to hold you because our time is over, but think about it and you'll see that, like, if you ask yourself, if I, and that's what Costa said, if I is the point of the dose of 1 and J is those of dimension 1 and 2, say, then it's really regular in the following sense. In the number of vertices of dimension 1 which are contained just in this, in the edges between 1 and 2 is indeed regular. So this side is regular. Like when we take the colors into consideration, then this simplicial complex is indeed a regular simplicial complex. Okay, so it has a lot of symmetry, even though it has kind of levels according to dimension. Next time, maybe I'll say something about the eigenvalues of it, or maybe I will go further. I'll decide. Well, let's see if everything takes more time. But on the other hand, I think these are kind of very basic and important examples that we should really